Hi everyone, you're watching the third lecture of EE635 Applied Linear Algebra. This would be the second module. So let me try and share my screen and let's get going. Okay, I hope this will start soon. Yeah, we're back. So, so far we have discussed this part that, uh, how converting a system of equations into an equivalent row reduced echelon form matrix, yeah, helps us get all the solutions in a very nice and easy manner, right? We saw this for the homogeneous equation. Yeah, we did this with an explicit example. Okay. What we are going to see in this module are some really amazing consequences of this row reduced echelon form uh, conversion of a given system of equations into this equivalent row reduced echelon form. Yeah, we'll call these observations, these consequences, as corollaries, right? So let us see our first corollary. Our first corollary is the following. Corollary number one. What is that? So suppose we have a homogeneous system of equations, Ax equals 0. Yeah, homogeneous is important, where A is some matrix of size as, like always, m cross n. However, here we make this particular situation, we insist on m being strictly less than n. So what does that mean? This means that the number of equations is strictly smaller than the number of unknown variables. Yeah, that is n, number of unknown variables is n, number of equations is m, number of equations strictly less. Right. Now, we say that this means, the corollary says that this means there exists, so this symbol means there exists x not equal to 0, it means non-trivial, not the 0 vector, such that Ax is equal to 0. In words, this means there exist non-trivial solutions to this equation. Why is that so? Proof is in fact very simple. So what are we saying? We are saying that m is strictly less than n. Now what do we know? We know that this, this number r. So let us say, okay, let r be the number of non-zero rows okay, in the row reduced echelon form of A, right? So I take A, I convert it to its row echelon form, and I say that, okay, there are R number of non-zero rows. So if R is that number of non-zero rows, then of course this implies this number R must be less than or equal to M, right? If this is less than or equal to M, this is certainly less than N, which then means, of course, this set gamma, which we have defined to be, 1, 2, 3, dot, 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 up to N minus, this is set minus. So you take the set and get rid of some numbers from the set. So here I'm taking away, okay, K1 dot, 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 up to KR. This implies this set gamma is non-empty. Yeah, because this has n number of elements. This set has r number of elements. R is strictly less than n. So I'm taking, smaller number of elements from a bigger set. The set has n numbers. I'm taking out r numbers away from it. So of course it will be non-empty. If it is non-empty, that means there will be free variables. This implies there exist free variables. Yeah, namely those variables which we had assigned, as we call, by the way, these numbers as these variables as parameters, the free variables. So here there will be n minus r such free variables, and because r is strictly less than n minus r is non-zero. So therefore there will be free variables, which means I can choose those variables to be non-zero. Yeah, that means it will be a non-zero solution. Yeah, that's it. This is the proof. Okay, this is going to be profoundly important for us. Yeah, this fact that if there are less number of equations and more number of variables, then every homogeneous equation will have non-trivial solutions. Yeah, so much important this thing is going to be that we're going to call this the star corollary or the star result. This will be our star result. We'll see this again and again. This is our star. So remember that. Fine. Now let us come to corollary 2. Corollary 2 is the following. Once again, I have equation ax equal to 0. A is a square matrix now. So let me write this a little differently. Let me write this way. Suppose A is a square matrix. This is given to us. Then Ax equal to 0 has only x equal to 0 as a solution. Only x equal to 0. X equal to 0, of course, is a solution. But suppose this is the only solution. There is no other solution. This is true if and only if A's row reduced echelon form is identity. Yeah, once again, proof is very simple. Let us see the proof. Okay. So this is an example of an if and only if statement, right? So as we will see quite regularly in this course, that for such if and only if statements, you have to prove both ways. You have to prove if, and you have to prove only if also. So in this case, what are we going to do? Okay, if and only if. So suppose let us prove the if part first. What does that mean? This means we assume that is RRE form is indeed identity. We have to show that Ax equal to 0 has only x equal to 0 for its solution, right? Yeah, this is what it means to show the if part, that if the RRE is identity, then x equal to 0 is the only solution. And in fact, it's very simple. Why? You see, Ax equal to 0, this is our system 1. This is equivalent to, by our earlier analysis, so this must be equivalent to system 2 with the RRE, which happens to be identity into x equal to 0. But this identity into x equal to 0 means x is equal to 0. That means this is the only solution. Yeah, right. Okay, good. Now we prove the only if part. What does that mean? Only if part means now I have to assume that x equal to 0 is the only solution, and I have to show that the RRE of A must be identity. Okay. Now, so for this, what I do is, so we assume x equal to 0 is the only solution. To show that RRE of A is identity. For that, what we'll do is let R be the RRE of A. So somebody has given me an A, and then I do this row operation business, what we have seen so far. Yeah, one by one, step by step I do, and I obtain this R to be its row reduced echelon form. Claim is it has to be identity. Now we see that this example of proof by contradiction, a very famous way of doing proof. Perhaps the first ever recorded proof of something by contradiction was the fact that square root of 2 was square root of 2 is an irrational number. It cannot be expressed as a ratio of two integers. Yeah? This was proved by one of the disciples of Pythagoras. Yeah? One member from the Pythagorean school of mathematics. Unfortunately, he had to pay by his life. Yeah, he was executed because Pythagoras is their school's belief was that everything is a rational number, everything can be expressed as a rational number. This thing actually struck a huge blow to that idea, that thought that everything is rational. Yeah, and that is why they were very uncomfortable with this truth, and this guy was murdered. Yeah, to that. But we are living in a much better world, we would like to believe, yeah, where rationality is not payable by death. Right. Anyways, so proof by contradiction. So what? How do we do this? So suppose this is not. So suppose R is not identity, right? But if R is not identity, that means what? That means, okay. So once again, let R be the number of non-zero rows in R. Okay, but then R must be less than or equal to n, right? This is a square matrix. Remember, this is a square matrix. So n number of rows, n number of columns. R must be less than or equal to less than or equal to n. Now tell me, can R be strictly less than n? Of course not, because if R is strictly less than n, the number of non-zero rows is strictly less than the number of variables, and our corollary one tells that there will be infinite, there will be non-trivial solutions there. That's a contradiction, because I've said that only trivial solution is the only solution, right? So then this cannot be true. If R is strictly less than n, then there exists non-trivial solutions by corollary 1, which is a contradiction. Which is a contradiction. Therefore, R must be equal to n. But if R is equal to n, then see what happens. I must have K1, K2. This is bigger than or equal to K2, K3, dot, 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 KR. But in this case, R is equal to n, right? So this is n, which is, so I have 1, 2, 3, 4, up to n numbers, which I have to distribute between 1 and n. They are distinct and they follow this order. Yeah, how is that possible? There is only one possibility, namely K1 must be equal to 1, K2 must be equal to 2, K3 must be equal to 3, and Kn must be equal to n. This is kind of reminiscent of that pigeonhole principle that you may have heard. Yeah, think about this. So I have n numbers, 1, 2, 3, 4 up to n. And I need k1 up to kn, once again, n numbers, which must satisfy this property that they are distinct and there is this order there. Yeah, how can we choose n numbers, n distinct numbers from a pool of n numbers? Yeah, there's only one possibility, namely this. But if this is the situation, then what we know about row reduced echelon form, the leading ones appear at these k1, k2, k3 positions. Everything in those columns must be 0. Yeah. So then what must be R? R must be, so k1 is 1, so 1 appears at the first position. Everything else in that column is 0. Then k2 must be 1, so 1 appears here. Everything else in that column must be 0. Then k3 must also be 1, everything else must be 0, and so on. So you understand what we are getting at, that this is nothing but identity. So row reduced form of this matrix must be an identity. Yeah, that is corollary 2. Corollary 3 is something that is actually related to this one, directly in fact related to this one. It's an addition to this equivalent condition, which is the following. Then RRE of A, so where A is a square matrix, so once again we start with A being a square matrix. A square matrix n by n, then RRE of A is identity. I'm just writing I here for identity. This is if and only if, we also write this, if and only if A is invertible. All right. What we mean by invertible? There exists a matrix B, which is also the same size, such that, notice carefully, AB equals BA equals identity. Proof. Yeah, once again, if and only if, so both directions I have to prove. First I prove this direction, which means we assume a row reduced echelon form is I, to show that there exists B such that AB equals BA equals identity. How do we do this? Well, see, I have A. Since A's RRE equals identity, I know that there exists a matrix M, which is a product of elementary row operation matrices, such that M times A is its row reduced echelon form, which happens to be identity. Yeah. Now, so that means I already have that M, which multiplies from the left and gives me identity. Such an M would be called a left inverse. Yeah. But now that's not invertibility. Invertibility means that there should be a right inverse also, and left inverse, right inverse should equal. We'll see later on that this is not always the case. Yeah, only for square invertible matrices, left inverse and right inverse both exist and they're equal. Yeah, so far you may have seen only one inverse, but there are these two inverses also. We'll see later on that there are cases when only left inverse exists, right inverse doesn't, or only right inverse exists, left inverse doesn't. Okay, but we'll see those things later. But now for this case, coming back to this situation where we have this M times A equals identity, so we have the left inverse, but what about the right inverse? Well, I know for a fact that, okay, let us do the following. If this is the situation, I multiply from the right by M again. That gives me identity times M, but I know from matrix multiplication that this means this has to be M again, right? But now I know that M also has a left inverse because M is a product of elementary row operation matrices. Since M is equal to actually something like EK, EK minus 1 dot 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 E1 elementary row operation matrices, there exists an M inverse which is defined as E1 inverse, E2 inverse dot 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 up to EK minus 1 inverse, EK inverse, all such left inverses. Each of them have a left inverse, namely the operation that undoes the row operation that you have done. Yeah, we have seen in the last lecture that for every elementary row operation matrix, there is another elementary row operation matrix that undoes that or undoes that, or whichever way you would like to call it. Right. This M inverse is a left inverse for M. So then if I multiply this equation, equation 1, so from equation 1 we get M inverse times M times A equals M inverse times M. This will become identity. This is AM equals identity, which means MA is identity, AM also is identity. So this M matrix is in fact is the inverse of the matrix A, right? So this goes to you as a homework. Prove that M is unique. And this inverse that I have created of this A in this situation is unique. Yeah. So we have proven this direction that if we assume that the RRE is an identity, then the matrix is invertible. What about the other direction? So here, okay, we assume A is invertible. A is invertible. To show that RRE of A is identity. This is in fact very simple. AX is equal to 0. X must be equal to 0 since A has inverse, right? B, A has inverse B. Let me write this a little more properly. Since A has inverse B, we get B times A times X equals B times 0. This is the same as X is equal to 0. So X equal to 0 is the only solution, but this implies RRE of A is equal to identity. This is by corollary number 2. This completes the proof of corollary number 3. Okay. Yeah. At this situation, so these are the three important observations that follow immediately from the star theorem that we have, sorry, from the row reduced echelon form that we have discussed, right? Now, one question might arise, in fact, should arise immediately, that what happens if there is a non-trivial right-hand side? What if we don't have only homogeneous equations? What happens then? Okay, I'm sure you may have seen this before. You must have called it, augmented matrix and things like that. But let us see what happens in the light of what we have seen so far. So recall, what did we have? So let me call this topic to be with non-trivial RHS, which is also known as inhomogeneous case. What happens then? So we have AX equal to B. This is my system 1. System 2, what I'm going to do is MAX equals MB, where this MA is R in RRE form. What does that tell us? Okay. Now, in this RRE form, so suppose this then is converted to Rx equal to, say I call it right hand side to be equal to D. In this Rx equal to D situation, how does R look like? So R looks like the following. This part is all non-zero equations. All non-zero equations. This are all the zero equations. This is R, this multiplies X, and this gives me, right hand side should be D. In this scenario, so this number is R. So how many such non-zero equations are there? R number of non-zero equations are there. Now in D, if I have, D also I say partition conformally. Yeah, I look at the first R equations. Whatever those first R equations are there, I can actually solve for them, right? Because I don't, just like, this is just like the homogeneous case. Only thing is that there will be a constant vector on the right hand side. So for each equation, I have, you remember, right? The first equation is xk1 plus summation ci, c1i, xi, I in gamma. Yeah, that was equal to 0. Now here it will be d1. Yeah, that's it. No big deal. I can solve for it. The problem will arise for the 0 rows. See, if I have 0 row here, but there is non-zero entry here, then the situation is like I have an equation where I have 0 times x is equal to non-zero. That is impossible. I have an equation of the type 0 into x1 plus 0 into x2 plus dot 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 plus 0 into xn equal to some number dr plus 1. Suppose this is non-zero. Then I have no solution because this is impossible case. It's impossible to satisfy. There is no exponent to xn that can satisfy this. When I have 0 times x1, 0 times x2 plus dot 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 0 times xn, that always will create 0. That can never create a non-zero number. That is the situation where we have no solutions, right? On the other hand, if these guys are 0, then however I will have solutions. And in that case, if there are free variables, then I will have infinitely many solutions. So these are the two situations that can arise. So in the D vector, if di is not equal to 0 for some I in the set starting from r plus 1 dot 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 up to m, then no solution. If di is equal to 0 for all I in r plus 1 up to m, then there exists solution. Yeah. In this case, if there are free variables, what is the condition for that? This is true when r is strictly less than n. Then there exists infinitely many solutions. Yeah, but how is that related to that augmented matrix thing that you may have learned before? Okay, that augmented matrix actually does codify what I've just mentioned here. How? Well, let's see. First thing, this number R of R equal to this number of non-zero rows in RRE of A. This is called the row rank of A, or simply rank of A. But right now, because we are doing only row operations and we have row reduced, that's why we have called it row rank. We'll see that row rank and column rank are in fact the same thing. One can define, but you know, you cannot just go ahead and define it like that and can say, and you say that, okay, row rank, number of independent rows, number of independent columns, they're the same thing. Yeah, that requires a proof. The basic definition is this one, that row rank. What is that? Do this row reduction, number of non-zero rows that you get, that is the row rank of the system, of the matrix. Yeah. Now, when I have A and also B, see, when I do this row operation, I'm doing on on A as well as B. I'm doing both. Yeah, it's just that I wrote it this way. I decided to write it this way. But if instead I write A and B like this, form this new matrix of size M and N plus 1. There is a matrix in M N plus 1 size. In this matrix, if I now multiply from the left by this M, this is a legitimate matrix multiplication. This is M by M, so it's okay. And the result is nothing but MA and MB. So that means this row operation that so far I have been doing only on the A matrix, there is no harm in doing that row operation on this AB matrix, which which you may have called as an augmented matrix before. Yeah, and may have put this dotted lines like that, but the same thing. This AB augmented matrix, which means if I start with AB and then I keep on doing these row operations, yeah, something R2 replaced with R2 plus alpha times R1, blah, 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 so on. We keep on doing this row operations, A1, B1, keeps happening, dot, dot, dot. Finally, we have, let's say, AK, BK, which is such that AK is in, so this finally is actually equal to row reduced form R and D. Then remember what you said. You said that there is no solution if the rank of A and rank of AB are different. What would that mean? You see, rank of R is small r always. That's the number of non-zero rows. If now D introduces a new non-zero row, yeah, when R has 0 rows, suppose the corresponding entry in D is not 0, then that means the rank of this matrix or this matrix as a whole has more number of non-zero rows than A had or R had. So then in that case, rank of, or rather row rank of RD, which must be equal to row rank of, let me write it properly, number of non-zero rows in RD bigger than number of non-zero rows in R. This is equivalent to saying row rank of AB is strictly bigger than row rank of just A. And that is the situation when we have seen that there are no solutions because there is an equation like 0 times x equals non-zero. And so this implies no solution. On the other hand, if number of non-zero rows in RD is equal to number of non-zero rows in R, and this implies solution. And if this number in this situation, if, let me write it here, if in this case um, this number R is strictly less than n, then infinitely many solutions. Yeah, I hope this clarifies that, you know, mystical thing as the augmented matrix and rank of augmented matrix and things like that. Okay, so I hope you have learned something new. Um, this time around, let's not do any. There is no immediate attention problem. Instead, I have given you only one homework problem. I think, yeah, this homework problem. You think about this. In the third module, we will see geometric interpretation of this, of what we have seen so far, right? Okay, so let's meet for that geometric interpretation in module number 3. Okay.